You are in that hallway. You are given. Now many companies even in India is doing it in the physical world. With our what you call ubiquitous connectivity and connected things, which is Internet of Things. This has got translated even into the real world, not just in the web. That's what. It's basically like kind of it's contextual, it's behavioral targeting and contextual targeting. Initially started with as two schools of thought. Contextual meaning like if you are in a page, that page will show you ads of that, right? Which is interesting. I don't want to. Primarily it's cookie based. You can clear the cookies and then there are many other what we call you pay pixel there are many technologies out there. It's every other day even your captcha is one too. I think 2008 times somebody has a patent. I think somebody from Israel. They got a patent to advertise on captcha. Right? If you get it right, if you do it multiple times, you are tagged. You get it right? You can also be tagged. So there are multiple mechanisms. It's not like it's not just. It was actually a cookie based, but it's moved much beyond that. So machine learning, the definition is from the classic book by Mitchell. I'll take another 10 minutes and then wind up. Feel of it. A program runs from experience. We have seen the data. It's experience with respect to some class of task. Task is make a cup of tea. Experience is your mom's experience. Performance measure is dad like it. As measured by P, because the dad should like it, then it's called a T, and then it has to improve with experience. You make more and more of P, and then you have to become there. Then only you say that you're learning. Right? This is a classic definition. So this is what we say. Right? From the experience, you learn to do a task. Task has to be done to the satisfaction with respect to satisfaction level with respect to a pre-set criteria, and then what? You have to improve, right? Over time to reach there. Then you say a system is learned. Building systems which can learn, right? The classic expert systems were not learning; they're just based on the rules. They suggest. Now the user gives the feedback. The system has to, right? People are building systems. But recently we also worked on something very similar to it for a corporate entity where we were trying to work on, and the avenue was predictive maintenance. You get it right? Predictive maintenance. Basically, engineers keep working on it. You log the data. You potentially know what to fail, what to be replaced, what point in time. You don't have to do a replacement, right? Unless otherwise, and you potentially have to give a confidence also in your decision. Such systems can be built. Related areas, I don't want to go there. Major paradigms here: supervised, meaning inductive learning. Training data includes the desired output. This is what we are seeing. Your tag is given. Unsupervised, there is no teacher. You start driving your car, you keep driving till you make an accident, then you say, no, I have not learned it properly. Otherwise, driven from Kashmir to Kanyakumari, then yes, looks like I have not made any accident, and nobody has scolded me, neither in Hindi or nor in Malayalam, meaning like the entire stretch. I was okay.
But that is supervised, like how do you know that?
It's not supervised. You do it. End of the day, you have done something, and the evaluation criteria will come there and say, okay, yeah, what you did is right. Nobody is going to guide the process.
What is the evaluation criteria? You have to mention that.
That's an interesting question. And in many unsupervised activities, typical example is clustering. There is no university accepted evaluation. That's what it is. If you want to look at it, clustering is a typical, or density estimation, you can say like how close you are to an expected density. That's what it is, right? And clustering, there is a classic tutorial by cluster validity measures. I think the author's name is HALDR. You get some statistical measures, and typically what you do is you say, okay, you group things together. An inter-group similarity has to be more compared to an intra-group similarity. How do you capture it statistically? Is what. But in the case of a supervised learning paradigm, say, let me give an example that I generally give to the class, which is I've got 20 terrorists and 180 common man, I mean very normal man, right? And I won't catch the terrorists. I call them the terrorists as a positive class. I mean I'm intent is to capture them, right? So what are the scenarios? I can capture a normal man as a terrorist as a normal man, and terrorist as terrorist, and normal as normal, right? Positive class is terrorist. So terrorist can be captured as a terrorist, that means a true positive is captured. A normal captured as normal, which is true negative is captured. Right? A terrorist captured as a normal man, this is terrorist captured as a normal man. What is it? Is it false positive or false negative? False negative. This is false negative, right? And the other way around is false positive. That means a normal man captures a terrorist is a false positive. So you can put it in a matrix and you can do whatever you want. Right? You can mix and match things, you can plot an ROC, say sensitivity, specificity, precision, recall, F measure, whatever. So classification validity measures and evaluation measures. You get n things. Every other day you can come up with new things also. Right? Then you say well defined. This is little. Third is semi-supervised. Meaning I don't have 5 lakh points which is labeled. No supervisor has given me this. What do you do? I have to classify documents as legal and medical. This is the scenario. I got 10,000 documents, out of which only 100 is labeled. 100 each. 5,000 typical I should get, that's a training document collection. 100 labeled here, 100 labeled here. How do I go about it? Semi-supervised. Yeah, that's basically like no manual cascade. Basically, he says one suggestion. That's one interesting. It's basically group all the points, right? Now in the box, you form like say 10,000 points, 1,000 points, whatever, right? 100 clusters. In the cluster, you see like there are medical and the other one, right? Which is maximum you can assign the cluster, right? Then you do a supervised classification. There are other approaches also. Basically, like there is a Bayesian approach now. Okay, no, just let me start the learning with these 100 each, 100 each, right? Once you do that, you get two classifications. You get two classifications. 100 each, you got two classes. You got a classifier. It's say medical or legal. Now I got another set which is unlabeled. Try to classify them. How to classify. Once you classify them, do it for retraining the classifier. Right? Retraining the classifier. Now you got a better classifier. When do you say you have converged? Converging means can you stop? Nobody shifts positions. This is no document going from this class. That's another. So, fourth one is reinforcement learning. Just give you a typical. It's another interesting avenue where what happens is like you are in an environment, you are an agent, you get reward for what you do. You do an action and you get reward. Right? Positive reward, what do you do? Right? Or else you do something else. This is a typical reinforcement scenario. Our agenda and these processes and these kind of problems are typically modeled what's called a Markov decision. You will have states, set of actions that take you from state to states. Then the probability of transition from a state A to S dash would be conditional probability. RSA is the expected reward. Your reward from S on A would be sum of S dash A, S to S dash by taking an action. Sum it up and the reward will. Right? You get it? And agenda is find the set of actions which will maximize your such learning paradigms do also exist. Right? That's it. If you want a little more, I can do I have time? Maybe 5 minutes more. I'll give you a very, since I told you I work on, this is a supervised paradigm, this is a figure I've taken from a book called Vladimir Vapnik. Let's assume that these are all pictures, photographer tagged this as a Maruti car, as a whatever, right? Say Hyundai car, Benz car, and likewise. This is a supervisor, teacher, tags it, photographer, teacher, tags it. Now, the learning algorithm. Algorithm has to learn to mimic the teacher. Algorithm will learn a function, f parameters by alpha. Alpha, in a neural network scenario, alpha is a set of weights. In the what do you call your probabilistic model, how do you fix the probability? It becomes the parameters of the distribution. So it becomes the agenda is this should match end of the day. And should not match exactly the training points because then you cannot generalize. Okay. So there is another classic algorithm which I just meaning you are in that powered way. You are given now many companies even in India is doing it in the physical world with our what you call ubiquitous connectivity and connected things with this internet of things. This has got translated into the real world, not just in the lab. That's what. It's basically like kind of it's contextual, it's behavioral targeting and contextual targeting. Initially it started with as two schools of thought. Contextual meaning like if you are in a page, that page will show you ads of that, right? Which is invest. I don't want to. Primarily it's cookie based stuff. You can clear the cookies and then there are many other what we call you pay pixel there are many technologies out there. It's every other day even your CAPTCHA is one too. I think 2008 times somebody has a patent. I think somebody from Israel. They got a patent to advertise on CAPTCHA. Right? If you get it right, if you do it multiple times, you are tagged. You get it right? You can also be tagged. So there are multiple mechanisms. It's not like it's not just. It was actually a cookie based, but it has moved much beyond that. So machine learning, the definition is from the classic book by Mitchell. I'll take another 10 minutes and then find out the feel of it. A program learns from experience. We have seen the data. It's experience with respect to some class of task. Task is make a cup of tea. Experience is your mom's experience. Performance measure is dad like it. As measured by P, because the dad should like it, then only it's called a T, and then it has to improve with experience. You make more and more of P, and then you have to become better. Then only you say that you're learning. Right? This is the classic definition. So this is what we are saying. Right? From the experience, you learn to do a task. Task has to be done to the satisfaction with respect to satisfaction level with respect to a pre-set criteria, and then what? You have to improve, right? Over time to reach there. Then you say the system is learning. Building systems which can learn, right? The classic expert systems were not learning; they were just based on the rules. They exist. Now the user gives a feedback. The system has to, right? People are building systems. But recently we also worked on something very similar to it for corporate entity, we were trying to work on, and the avenue was predictive maintenance. You get it, right? Predictive maintenance. Basically, engineers keep working on it. You log the data. You potentially know what to fail, what to be replaced, what point in time. You don't have to do a replacement, right? Unless otherwise. And you potentially have to give a confidence also in your decision. Such systems can be built. Related areas, I don't want to go there. Major paradigms here. Supervised meaning inductive learning. Training data includes the desired output. This is what we are seeing. Your tag is given. Unsupervised, there is no teacher. You start driving your car. You keep driving till you make an accident, then you say, no, I have not learned it properly. Otherwise, driven from, Kashmir to Kanyakumari, then yes, looks like I am not made any accident, and nobody has scolded me, neither in Hindi or nor in Malayalam, meaning like the entire stretch. It's okay.
But that is supervised, like how you know that?
It's not supervised. You do it. End of the day, you have done something, and the evaluation criteria will come there and say, okay, yeah, what you did is right. Nobody is going to guide the process.
But what is the evaluation criteria? You have to mention that.
That's an interesting question. And in many unsupervised activities, typical example is clustering. There is no universally accepted evaluation criteria. That's what it is. If you want to look at it, clustering is a typical, or density estimation, you can say like how close you are to an expected density. That's what it is, right? And clustering, there is a classic tutorial by cluster validity measures. I think the author's name is HALDI. You get some statistical measures, and typically what you do is you say, okay, you group things together. And intergroup similarity has to be more compared to an intra-group similarity. How do you capture it statistically? Is what. But in the case of a supervised learning paradigm, say, let me give an example that I generally give to the class, which is I've got 20 terrorists and 180 common man. I'm a very normal man. Right? And I won't catch the terrorists. I call them the terrorists as a positive class. I'm intent is to capture them. Right? So, what are the scenarios? I can capture a normal man as a terrorist as a normal man, and terrorist as terrorist, and normal as normal. Right? Positive class is terrorist. So, terrorist can be captured as a terrorist, that means a true positive is captured. A normal capture is normal, which is true negative is captured. Right? A terrorist captured as a normal man, this is
Negative.
terrorist captured as a normal man. What is it? Which is false positive or false negative? False negative. This is false negative, right? And the other way around is false positive. That means a normal man captures a terrorist. It's a false positive. So you can put it in a matrix, and you can do whatever you want. Right? You can mix and match things, you can plot an ROC, say sensitivity, specificity, precision, recall, F measure, whatever. So, classification, validity measures, and evaluation measures. You get N things. Every other day you can come up with new things also. Right? Then say, well defined. This is little. Third is semi-supervised. Meaning, I don't have 5 lakh points which is labeled. No supervisor has given me this. What do you do? I have to classify documents as legal and medical. Right? This is the scenario. I got 10,000 documents, out of which only 100 is labeled. 100 is. Right? 5,000 typical I should get, that's a training document collection. 100 labeled here, 100 labeled there. How do I go about it? Semi-supervised. Yeah, that's basically like, no manual classification. Basically, he says quantization. That's one interesting. It's basically group all the points, right? Now, in the box, you form like say 10,000 points. 1,000 bodies, right? 100 clusters. In the cluster, you see like there are medical and relevant, right? Which is maximum you can assign the cluster, right? Then you do a supervised classification. There are other approaches also. Basically, like there is Bayesian approach now. Okay, no, just let me start the learning with these 100 each, right? Once you do that, you get two classifications. You get two classifications. 100 each, you got two classes. You got my classifier. Say medical or legal. Now I got another set which is unlabeled. Try to classify them. Forget classify. Once you classify them, do it for retraining the classifier. Right? Retraining the classifier. Now you got a better classifier. When do you say you have converged? Converging means that can you stop? Then nobody shifts positions. This is no document going from this class. That's another. So, fourth one is reinforcement learning. Just give you a typical. It's another interesting avenue where what happens is like you are in an environment, you are an agent, you get reward for what you do. You do an action and get reward. Right? Positive reward, what do you do? Right? Or else you have to do something else. This is a typical reinforcement scenario. Our agenda and these processes and these kind of problems are typically modeled what's called a Oppurtunities process. You will have states, set of actions will take you from state to states. Then the probability of transition from a state A to a state would be initial probability. RSA is the expected reward. Your reward from S on A would be sum of S dash to S dash by taking an action. Sum it up and the reward. Right? You get it? And agenda is find the set of actions which will maximize your such learning paradigms do also exist. Right? That's it. If you want a little more, I can. Do I have time? Maybe 5 minutes more. I'll give you a very, since I told you I work on, this is a supervised paradigm, it's a figure I've taken from a book called Vladimir Vapnik. Let's assume that these are all pictures, photographer tagged this as a Maruti car, as a whatever, right? Say Hyundai car, Benz car, and likewise, this is a supervisor, teacher, tags it, photographer, teacher, tags it. Now, the learning algorithm. Algorithm has to learn to mimic the teacher. Algorithm will learn a function f parameters by alpha. Alpha in a neural network scenario, alpha is a set of polynomials. In the what you call your probabilistic model, how do you fix the probability in terms of the parameters of the distributions? It becomes the agenda is this should match end of the day, and should not match exactly the training points because then you will not generalize. Okay. So there is another classic algorithm which I just get to Google Scholar. So support machines have published papers like multi-class correct machines, lot of support machines, lot of support clustering, adaptive active learning in support machines. There are many such papers out there. Clustering papers, primarily I would say algorithm design. Who keeps an edge on applications also because that's where I apply algorithm to machine learning also. My primary interest is kernel-based machine learning. That's where classic examples are. So currently I do research on what is called deep learning, right? You must have heard of it. I do work on deep learning and semantic extraction from statistical models. This is what Google is trying to do. We have statistical models out there. How do you infer semantics from statistics? Can you combine a little of linguistics into statistics? Semantic structures from semantic structures, stats. You have some basic research and publish somewhere. You get it.
Some other elements, like, so with the availability of platforms like Amazon machine learning and Azure machine learning and
Mahao and all that.
And
So people like us contribute to it.
IBM works in that. So do you think the barrier for entry
Is very low now.
very low?
It's very low. If you are a user, a business, the entry barrier is very low. You have it. That's why I said you don't have to learn all SVMs. And that's the reason why I've not started with few equations and started talking here. This is a typical academic talk. I was not doing that. I didn't want to do that. I can write some equations, solve this, and on this. This is W like this. You have optimizations, a quadratic program, do this. No, you don't have. You don't need it. Go download the SVM Lite. They have statistics. Entry value is low. So we have contributed that to that also. How we have an algorithm for receiving is our contribution. That is very basically Watson is a very generic platform. We have beaten Watson in one of the projects, consultancy projects, quite recently. You got it right. Watson is generic, so generic.
It's not for NLP.
It's statistical NLP for none. It's computational linguistics. It's called computational. It's a computational engine. You have seen Wolfram Alpha. It's a computational search engine. Not a search engine, computational engine. Wolfram Alpha. That does a better job than Watson. It's from the same. It's from the founders of Mathematica, Professor Wolfram and so entry barrier is low. Algorithms are simple. Open source is available at all. I mean, you can just download Becca and use it. Becca is from University of Becca. So what we do is actually contribute to the science. And at times people come back to us with problems, and we map that to probably existing algorithms, and then say like, that's our approach. Look at the problem, identify the mathematical part of it, identify the problem mathematically, and see whether there is an open source implementation. Then you go use it. Otherwise, we modify the algorithm and say like, take this open source, modify this part of the algorithm, like this, or we modify it and do it. So you get another experience. That's what we do. It's not the other way around. I mean, what typically happens is, people will go download some open source, they have a problem, knows that this is a classification problem, experiment a lot with it, and they realize that nothing is going to work, they'll come to us. Right? So they know that there is LibSVM, there is SVM Lite, there is Becca, there is what we call Psych of Python and all that. Then they fail. Because they don't understand the problem. We start the problem. Implementation, we use only when we don't know to implement. We know that we need naive, that's it. Naive is there, take it. Because this can be solved by naive. Correct? Yes. Any other?